Today, we're going to be diving into a very interesting subject that I don't think you'll find a lot on elsewhere, which is evolving neural networks through augmenting topologies. And to me, this is pretty neat in more ways than one. Diving into this research paper was written over 20 years ago in 2002. And this research paper essentially breaks down an algorithm that we're going to reconstruct to create evolving neural networks that can adjust their own parameters, their own weights, adjust everything about the neural network itself based off of different conditions, just like typical evolution. And what we're looking at here is that. But before we dive into this actual code and what we're looking at here, I want to dive into kind of the like philosophical and scientific arguments around this, right? So, like, kind of the first question is why is someone like me interested in these concepts, right? Like evolving neural networks and swarm algorithms, genetic algorithms, all of these types of things. So I'll start there. And so to me, it's very simple, right? When it comes to AI, I look at this as our first attempt, like what our model is, the ultimate model is the brain, the human brain, right? Um, that's the ultimate model. What we know that it is possible to get to. And so as an example of that, the human brain operates off of 20 watts of electricity total, meaning that there are light bulbs that require more electricity to power than your brain. And your brain is more powerful than any computer ever invented, more like a million times more powerful than ChatGPT. And ChatGPT operates off of gigawatts, literal nuclear power plants to power ChatGPT, as opposed to your brain, which can be powered with less than a light bulb. And so there's a massive gap there, right? Nuclear power plant to less than a light bulb. How do we close that gap? I don't know, but that gap exists, right? And so within that, if we're following kind of this biomimicry framework, then we have a long way to progress. That's step one. Two is that I don't at this point think that it is necessarily the best approach to 100% stick to biomimicry. I think that we should. It's important to utilize biomimicry and certain aspects. Like we wouldn't have neural networks now. We wouldn't have transformers without perceptrons. We wouldn't have perceptrons without neurons. We wouldn't have neurons without understanding how it works. But well, how it works today is not how the brain works. The brain doesn't have backwards propagation, for example. The brain doesn't utilize an attention mechanism per se. There are elements of AI that have been put into AI just because they work for AI. And so we've kind of gone away from biology in that sense, but it still works. And then so to me, what that means and how I correlate that is that so we have the number one example that we should be shooting for, right? The human brain, like the unobtainable. And we have on the other end this understanding that we shouldn't be 100% adherent to the human brain, but that leaves us a lot of play to go in different directions and to explore different scenarios within that. And then, so to me, the biggest scenario to explore is how exactly is that energy efficiency obtained? Uh, I want to explore that question in depth. And I don't like LLM models will never, ever, 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 ever be that. It's just the way that it works, right? LLM models are mathematically inefficient. Like that's the bottom line. And there's no equation that will ever get around that, around exploding gradients problems with the attention mechanism, which is the biggest problem within this, right? Like mathematically, attention mechanisms and transformers aren't it. They're just not. And no mathematician will ever argue with that fact because of the fact that they're just so computationally inefficient. ChatGPT takes a nuclear power plant to run because it's such exploding math problems, right? It all comes down to the math. And then so on the opposite end of this, you have evolving neural networks. And then to me, this is like kind of the secret sauce. This is where you start getting into how exactly does the brain operate with 20 watts. It's something like this. And so diving into this neat evolving neural network, it's very straightforward as to the biomimicry, right? And then so let's rewind in time. It's 2002. And so we're very far behind in regards towards current AI and current computing knowledge. And so all of this is based 100% still off of biomimicry. We're still in that phase, right? And it's important to note in this phase, in this 2002 phase, that we don't have, like, computers aren't utilizing parallel processing. and that term, like parallel processing, is just starting to come out. I know this because I'm working for Intel during this time, and then they're working on the technology that's going to enable this in 2002, but I don't start talking about it until 2006 or so. And then so going through and diving into exactly what this does is very straightforward. What we're doing is we're creating so we have a population size here of 150. And then so that's we're creating a very small neural network with 2 input layers and 1 output layer and 0 hidden layers. And we're utilizing a feed forward network. We're giving it all of all of the details for a neural network. And then in this instance, we're then giving it its initial weights. And then we're also including all of these. You'll see these arguments for mutation power, like mutate power, mutate rate, weight mutate rate, weight mutate power, etc. And then so all we're doing within this is we're creating essentially random parameters, really random parameters for this neural network to evolve itself, right? So we're saying, okay, you're a neural network, and then your fitness criterion is that you want to maximize the fitness criteria. And then in order to maximize that, you have your score, your goal is to optimize the fitness rating to a score of 3.5. So that's what it's trying to do, right? So we have to give it a goal to work towards. And we say, hey, work towards this goal. Here's a bunch of random parameters and a bunch of random mutations. Take your population, and then we're going to go for 60 generations in this instance, and then we're going to iterate through. And then I'm going to hit play on this cell. Boom, we see it took 2 seconds to execute, right? What do we get out of that 2 seconds? All of this. And that's, so I'm going to start scrolling. I'm going to show you how much this is 2 seconds. Watch. Still going, 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 still going. I got all of this. And then so if you compare this to the inference of LLM models, you see a massive difference here now. You see computationally, an LLM model will never, ever, 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 ever be able to compete with this, right? And with this algorithm. And then this algorithm literally ran for 60 generations. It did all of these mutations, and we can see it's mutating every single time. We see our fitness going up, and our fitness score is decreasing. So it starts off as a -2, immediately drops to -1.1 off of just one mutation, and then it gets stuck here, 0.7 for a long time. And then we get some mutations, like for 17 generations, look, and then we start getting mutations again, and then boom, 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 and then we start getting a lot of mutations, and then it's like a massive adjustment, right? And as we can see, the score is adjusting dramatically at this point. And then so now we're up to almost 0.5, 0.58. And we see that there's just massive fluctuations in this score. And then all of a sudden, massive mutations happening as a result. And then where we're seeing a lot of stagnation, all of a sudden we just see massive growth out of nowhere. And then we, at the end of the day, we find that generation 49 ends up out of these 60 generations, ends up being the best generation out of these. And then it gives us, here's the parameters and the outputs from that generation 49. And so, within this, I have here it's very straightforward as to how this library works, first of all, right? So it's just this pip install of the neat Python package, and then I'm running, this is my argument for, essentially, this is your argument for your fitness function. That's all that this argument is. It's defining the fitness function, and then it's loading our configuration file here. And you're running. And then if you'll notice here in this Colab notebook, I have it for you. I've copied the config file and then and let me fix that. But so I copied this for you. So within Colab, once I close this notebook, this my config file is going to go away. And then so what you're going to want to do is you're going to want to go into your notebook. It'll be closed here, files, and then right click, new file. You're going to want to label it neat config. And then you're going to want to go down to exactly where I have my config file here, and then just copy and paste your whole config file, and then recreate this neat config. And then within this, you'll be able to run and execute all the code that you're seeing here. And this will allow you to get your genetic algorithm. And then so this genetic algorithm, I mean, to me, this is super cool. This is 2002 technology, and we're already here, right? But this genetic algorithm is running through, it's iterating on this neural network that we've created, and it's literally refining the neural network, giving us improvements, right? And then scientifically speaking, with a typical neural network, what I would do is I would go through and I'd randomly assign these weights, and then I'd adjust based off of like testing and different things, right? This algorithm is taking care of all of that for us via just simple mutations. It's an evolutionary algorithm, right? And then so to me, the key takeaways within this are nature wins every single time, right? So this algorithm that we're looking at here, this is based off of nature, based off of evolution, and my assumption and these people's assumptions as to how evolution would work if we were to create it as a pure compound function. Well, it is very, very, very computationally efficient. Runs in pure seconds, updates itself. This is, in terms of what this does, a LLM model will never be able to achieve this. This is light years away from the LLM model, right? It's again comparing like the nuclear power plant to like the light bulb in terms of power and power consumption. And then to me, we need to get more and more focus on these areas. And then so this is where I spend more and more of my time. That's why I'm making more and more of this type of content. And I hope that you like this neat evolving neural network. I'm happy to discuss this further. And if you like this type of content, please like and subscribe. Thank you very much.